Let's get started with the talk. This is actually going to be more than just a talk and probably a fitting end to the Congress. So we have Capayod, who is going to give a live demonstration of the security vulnerabilities of the real-time transport protocol. And he has a live setup here, which is pretty much going to be his talk. His talk is going to be a demonstration of the kind of vulnerabilities that the protocol is prone to. So yes, let's begin the talk. Yeah.
Okay. Thank you. My talk will mainly focus on the demonstration part. At first, I will be giving this some overview about RTP and for what it's used and what might be the problems with it. And the demonstration will focus on the asterisk open source PBX because for like the last 8 to 9 years, that's what I've been doing from day to day. But I've also tested it with different other open source implementations and will say a few things about that. So that's just the overview. We just dive into a very short introduction to RTP. It expands to the real-time transport protocol. The first version was RFC 1889, and that's the recent version is RFC 3550, just if you want to take a look yourself at the specification and see what's in there. Basically, it's just used to transfer multimedia streams, maybe audio or video, over an IP network, usually using UDP as a transport layer for that. And because networks, especially like the internet or wide area networks, are lossy and support that packets may go to the same destination over different routes, they have added support for reordering of packets by using sequence numbers, and also the RTP conveys the timing of the sender to the receiver, so it can basically synchronize to the clock of the sender and then sample the audio or the video and then play it back. It's mainly used nowadays with voice over IP signaling protocols, H323 or SIP, which is probably like 90% of what is being used today, but also other protocols like MGCP, and I also think STCP from Cisco is also using RTP. So it's very common. It's basically what is used in most cases when people are using internet telephony over the public internet or just private networks. And actually, it's two protocols. It's RTP, the real-time transport protocol, and RTCP, the real-time transport control protocol. But most people just refer to both protocols by, well, we're using RTP, they say. And the specification says an RTP usually runs on an even-numbered port, and the RTCP usually runs on the next higher odd-numbered port. But I think that's not required anymore with the new version, but it's a very good idea to do it so your implementation is backwards compatible with old implementations. So if we look at an RTP packet, basically it's just an IP packet with a UDP header inside, and then we get at least 12 octets of the RTP header. I'll just go over it very quickly. Basically, you have a version number, which can be 0, 1, or 2. 2 is the actual version that is used. RTP version 1 has been not really used, and there are no plans for a new version of that. Then you have some indicators like if there is any padding applied to the packet, what type of payload the packet contains. That usually is it is defined by different profiles of RTP. The main profile that is used is the audio-video profile, AVP, or the secure audio-video profile when you're using secure RTP. Then we get to the interesting stuff. That's a sequence number, so you can reorder packets if they arrive in a different order. It's just a 16-bit counter, which will also wrap quite often. And the payload that is contained in the packet, the first octet of the payload has been sampled at the sender at this timestamp, which is a 32-bit value. It's a good practice to, when you start a new RTP session, to use a random value for the timestamp and the sequence number. to work against plain text attacks when you're using SRTP. You already got a question? For example, if you're using a G711, then you have like, it depends on the sampling rate you have, but usually you're using 8 kilohertz. And then you have like 8,000 bytes per second. And every byte of that is one increment to this timestamp. So for audio, it wraps, I don't know, not that often. But if you have a video application, it will wrap quite often. That's why usually if you have a good RTP implementation, you will maintain a 64-bit counter for the timestamp and at least a 32-bit counter for the sequence number, which is only 16 bits. It will also wrap around quite quickly then. But many don't use that. But that's usually not so much of a security problem. But it's important that you use a random value when you start with your session, because if you're using SRTP, and it makes it much easier to do plain text attacks against the packets, because you know, okay, it starts, this will be 0 in the packet and this will be 0, so you should use a random value. One of the also important headers is this synchronization source. That's basically a 32-bit random value that is chosen for each participant in a session. And basically this identifies the sender of the packet. I'll be getting to the SSRC on the next slides, especially in the demonstration. Then you have some optional headers that, for example, if this packet comes from some kind of conference bridge, then there might be not only one SSRC involved, but several participants, and they are also part of this header. But on usual one-to-one calls, you don't have those optional headers. You just have the 12 bytes. And when you're using a frame size of 20 milliseconds, that results in 16 kilobits of overhead, which you already have. And then you have to add your codec bandwidth to that. Many people often forget about the overhead of RTP, and it doesn't make too much difference if you're using G729 with 8 kilobits or GSM full rate with something like 12 or 13 kilobits of payload, when you always have the 16 kilobits, so it doesn't make too much of a difference. Okay. The most problems arise when you're using, or when you're trying to use a SIP phone behind a network address translation to connect to some public SIP server. Because in the SIP protocol, when the session is negotiated, both sides just send an SDP message which says, I want to receive my RTP on this IP address and port. And if the device is behind network address translation, it doesn't know the external IP address, so it puts in some internal IP address into this message. And then you have the typical case of one-way audio. What you send out to the SIP carrier usually gets through, because they have an official IP address, but the way back, and you don't get any audio. And to work around that, you can either have like on the router, have a SIP-aware software that looks at the SIP packet, does packet inspection, and sees there's an SDP with RTP going to this internal IP address. I will map this to my external IP address. Maybe I will keep the port or use a different port. And then the audio that's coming from the SIP carrier will go through to the phone on the local network. The other option is that the SIP carrier will do the NAT traversal for you. So basically, it will not start sending packets before it gets the first packet from the device behind the network address translation, and then it will just reply to that. And so the outgoing RTP from the SIP phone creates a NAT binding, and the server can reply to that with symmetrical RTP. But the RTP specification does not really tell you that the RTP that you are receiving will be coming from the same IP address and port that you are sending to. But most implementations just assume that this is a fact. But it's a fact in the case in like 90 or 99%, but the RTP can come from somewhere else. And then we run into problems. Most implementations think we choose the RTP port, on that we receive the audio randomly, and we use a port range of like 10,000 or 20,000 ports, and it's very unlikely that you might hit one of the active ports if we are only like pushing 4 or 5 channels. So usually nothing bad happens unless you are in a scenario where you have a lot of calls on a single machine, and that's how I get the idea of how this worked, because a customer had people complaining that they heard a second call in their RTP session. Of course, the audio was a bit messed up and chopped up, but they heard a second call, and that was due to some messed up software phones, like I think it was some old version of SJ phone running on Windows, which just didn't stop sending RTP after a call was gone. So it just sends the audio from the microphone, and well, if you have 2,000 users on that PBX and you have only a port range of 10,000 ports, half of the ports go away for RTCP, so you're left with 5,000 ports, and then it happens that you will get distorted audio. And that's how I got the idea to look a bit at the implementation of Asterisk, of course, because that's what I'm doing from day to day. And I wanted to know, how does this NAT traverser on the remote side work? So I looked at it, and basically when an RTP packet is received on a port and there is an active RTP session, then Asterisk will just override the return address for that session with the address that the packet originated from. And it really doesn't check the packet very well. So you can even send RTP packets that don't contain any payload. So you just send the 12-byte header, and you send them like very often, every 2 to 10 milliseconds. So you make sure that you will override the return address, because the original RTP peer will only send every 20 milliseconds or 30 milliseconds one packet. And then you can make sure that you will get the answer from the other side. And this doesn't take very much bandwidth, because you're just sending 12 bytes. You can easily scan a complete range of a server. Usually you know that the port range, the standard is 10 to 20,000, but you can also scan from 1 to 65,000. Yeah, it doesn't take much time or much bandwidth. And it's not easily detectable because, well, it just looks like RTP. And nobody is usually looking for that. When they have some audio problems, they're usually looking for congested links or somebody sending lots of data to some ports. So it's quite easy to hide that you're scanning this. And I've made a very simple and crappy program in C, which just takes that port range and starts scanning and outputs, okay, I got a response. And afterwards, then you can get to the fun of doing denial of service or some other nice things with it. And of course, you also receive the RTP from one of the parties, and then you can look at this SSRC, the synchronization source identifier. And also, you can then say, okay, I get RTP on port 10,000, so I will get RTCP on port 10,001. You start sending the same packets, you get the RTCP, and RTCP is used, for example, to tell the sender of an RTP session, okay, I'm receiving you with jitter X and dropouts of whatever and that latency. And this receiver report that the other party is sending contains the synchronization source of the original stream. So then I can look at my RTP ports, get the RTCP, and then I see, okay, this RTP port is talking to this other RTP port. And then I have the conversations mapped one-to-one. And if I really want to put up some effort and have a good network connection, then I can just, if I use a very good timing, then I can play man in the middle, because I will send packets without payload to override the return address. And when some real packet is coming, I will get that packet, send it to the other session, and if no packet is coming, I will just also send those packets without payload. And basically this way I can be man in the middle, but I'm on the public internet. And especially with asterisk, there is no option to bind the RTP to a certain IP address. So it binds to 0.0.0.0. And that way you have, for example, two phones in your local network. You have your asterisk server that's connected to the internet because you're using a SIP provider. And somebody else from outside the internet can see that there are two phones talking on the internal network, and he can be man in the middle from remote. And that's quite fun, but I was too lazy to actually implement that. So we'll have a few more simple demonstrations, but they show what you can do, and then maybe you can do this as your homework to implement something like that. What I'm demonstrating is I have an embedded system here, some x86 PC Engines box with 3 network interfaces. 2 of them are bridged together as a local network. And the third one is basically the internet connection. Now it just has a static IP address connected to my network. And it's running the recent 1.6.2.16 RC1 version of Asterisk, the stable 1.6 branch. And it's just configured so I can make calls between the 2 phones. And I'm remote. It's not like we're doing something like ARP cache poisoning and then getting to the RTP on the local network. That's like maybe 10 years ago. That's very easy. Just turn the switch into the hub and then do man in the middle or whatever. Okay, so now I'll try to my terminal. I can't see it here on my netbook, so this might get a little tricky. But at first I will SSH into my asterisk. 10.0.0.1. Okay. I haven't started it yet, so I just start asterisk. And then does something strange with the colors. In version 1.6 and version 1.8. Then see if my SIP phones have registered. Probably not yet, because asterisk was not started. So we might need to reboot the phones, but no problem. And the external network is 10.0.0.1, and internal I have 192.168.192.1. And the phones register to this internal network, and I'm looking at it from the outside. So they need a bit of reboot time, but it should be fine. As I'm not very creative with giving names to software, which if you know me, you might know that I do stuff quite a lot. Put in the IP address, and to speed up the demonstration, I have limited the RTP port range from 10,000 to 12,000, but you could easily implement this and send lots of packets in parallel, but I'm lazy, and so we'll stick with 10 to 12,000. Okay. A bit difficult if you can't see it. The phone's still booting, so if you got any questions in between, just the question was what phone I was using. It's a SNOM 300 SIP phone, just because they are not so big, so I could easily fit them into my bag. But it's just a standard SIP phone. One of them registered yet? Not registered, which is a bit strange. This one is registered. Okay, the other one is registered too. Of course, to make this work, we have to enable net traversal. which you normally wouldn't need in the local network, but a few people quite like to take their phone home or use it remotely, or they have a central S3 server somewhere in the data center and then just connect the phone from some ADSL line. So a very typical configuration is in zip.conf to enable make it register dynamically, and then also don't allow re-invites because this will not work with NAT, and also do not allow to set up direct media between the phones, also doesn't work. And of course, NAT equals yes, so you turn on the NAT traversal. Okay, then I'll make a phone call from 100 to 101. Okay, should produce some nice feedback. Okay, I'll put that to the side. Now the call is running, and then from my netbook, I will just now start scanning the port range. Hopefully, yeah, we already found one session. It should be enough. The first thing I will be demonstrating is just plain denial of service. Basically, the program I'm using is sending lots of packets with an actual payload of G711, 160 octets, and this will be forwarded to the other phone. But also, I'm overwriting this return address constantly, so the answer from that phone is going to me. So there is not one-way audio, there is no-way audio. Do this just with RTP, gem, at the internet address and port. What was it? 10.326. I think there was some 326. Yeah, okay. That's difficult. Okay, we turn on the speakerphone again. And we'll have some feedback there. And now we don't have any feedback anymore. And if I stop it, then we will have nice feedback and no feedback. So this is denial of service, which is quite easy and can be quite effective because you know just what port you have to send packets to, well, not make them do any phone calls anymore. It doesn't work perfectly. You sometimes hear the feedback because, well, the program is just a proof of concept, so that's not important. And now we like to do something else. A lot of people, when they're using asterisk, also allow calls to be transferred using DTMF. This is quite useful. For example, if you forward calls to your mobile, then you're able to just press star or pound and then an internal extension to redirect the call in your PBX, which is usually not that easy with a mobile. I've also set this up, and now I will just inject DTMFs to that port. 326. We want to send DTMF, and for example, we can turn on the speaker and we send a 1. Don't hear that, but I think is it the right port? Okay, now I've sent the pound sign and I can transfer the call. Okay, I'll do that again. And then I transfer it to extension 9, which could basically be my 0900 number registered in somewhere in Africa where I get my kickback to, well, just what the guys did in, I think, Romania. They got caught a few weeks ago with 11 million euros of damage, and that's pretty easy to do then. Okay, and to do the man in the middle, you really have to have a good internet connection to that asterisk server, because if you have lots of jitter and packet loss, then it will be quite difficult to produce this correct timing to always override that address. Well, that's so much for the demonstration. Of course, you can think of strange other things that you could do. You could send like a fax tone to trigger a T38 re-invite or something like that, or yeah, just send some audio to some annoying message that this call is whatever interrupted, and you can make up some business model with that, I'm pretty sure. And also it's the most, the nastiest way is just to disrupt some calls a little bit of your competing SIP carrier or whatever. Just make it a crappy quality, and then, well, you might win some customers. Okay, and that's what I've just been demonstrating. You can think of different other creative ways to do this. If you want to do man-in-the-middle attacks, just do it. It's very easy. No, it doesn't. I've tested it also with other things. And let's go to this one. For example, I mainly tested this with all versions of Asterisk. And I also tested RTP proxy with the recent version 1.2.1, which is quite common, used by people using OpenSIPs together with an RTP proxy. And what I found is a bit more strange than Asterisk. When I was scanning the port range of RTP proxy, I sent one packet, I hit the RTP session, and from then on, I got all the RTP. And it didn't recover unless you would do a re-invite on the SIP phones, and afterwards it was not possible anymore to redirect the RTP. So somebody should take a look there and do something about it. And I've also done some, let's say, research on the public internet and found people using RTP proxy, and they sent me like a few hundred megabytes of RTP, probably some test calls that have been set up, and yeah, it takes some effort to work against it. But I've also tested like regular SIP phones. When you have a SIP phone, it's not possible to find the port on which RTP is running. But I was interested to see if it's possible to do a denial of service against a SIP phone when you know the port. Because actually you could do some validation of the RTP stream coming in. At first you look at the version number, is it 2? Then you look at the sequence number, is it increasing by 1 with every packet? Is the timestamp increasing by 160 if you're running G711? And is it coming from a different IP address all the time? But they don't. So basically with every SIP phone, you can, in my test program, I'm actually sending with every packet a random sequence number and a random timestamp, which should never make a valid RTP stream. But I can use it to disable the audio on SNOM SIP phones, probably on Cisco. I tested this on Linksys, ATAs, and it really isn't that important for a phone to do it, because it's not that easy to find the port. Unless you limit the RTP port range of the phone to like 4 ports, because you want to forward it through your firewall or something like that, and then it gets a bit difficult. No, I want to go back. So I thought about a few ways, what can we do? Actually, with Asterisk, there is a way. You can just configure strict RTP equals yes in RTP.conf, which is disabled by default, probably because people are afraid of one-way audio scenarios, which can happen when you enable that option. And what it does, it basically limits the time frame where you can overwrite the return address of the session to the first few packets of that session. And this can create problems. For example, if you have an external music on hold server and you're not really re-inviting the session to make sure that the audio is coming from that music on hold server, then you won't get that music on hold, for example. I also think this is the main reason why the SIP phones basically take RTP from anybody, because it's convenient to have some sort of music on hold server, and then you just say, okay, send to that phone, to that port, and then it will render the music on hold. But actually, it's not the best idea. So with Asterisk 1.6 and 1.8, you can just enable that option. but then you would have to check if everything works with calling over SIP carriers over the internet, and I think they didn't want to have too much trouble, so they added the option, but it's disabled by default. For the older versions of Asterisk, there is no solution. You can just not use NAT traversal with it. So one thing would be to use a VPN to get rid of NAT. Even some of the bigger SNUM phones have a firmware which includes OpenVPN, which also gives you like good encryption, which Asterisk doesn't have until Asterisk 1.8 because it doesn't support SRTP. And of course you could say, okay, why not use SRTP? Because then it's encrypted and then I can make sure that I can decrypt it and it's coming from the correct source. And I tried this some weeks ago with Asterisk 1.8.0. It might have changed by now, but I sent up an SRTP call between two phones that got NAT traversal on the Asterisk, and then it just needed a single packet to one of those ports, and Asterisk would say, this is not the SRTP that I'm expecting, and it hangs up the call completely, which is, well, nice. So the other nice thing which you could do and which mainly corporations do is have a firewall that is SIP aware and does SIP packet inspection, and then it will just open those ports to the internet where they will be expecting RTP from a SIP carrier. But this works, but with some firewalls it can happen that the firewall SIP inspection isn't that good to detect that the call is over, and it will just leave the port open. And then if you make like a few thousand calls with random ports all the time, at some point of time you will have the complete port range open, and well, it just buys you time. Maybe you should restart the firewall every day and then you're fine, sort of. Yeah, and if you want to get into the implementation, then it gets, well, there are things you can do. Just do not accept packets from a new IP address when nobody told you so. Usually you would accept packets coming from somebody else when there was a re-invite to the session or when something changed. But this, of course, makes the implementation a bit more complicated. And for example, in Asterisk, the RTP support is like really old. And nobody looks at like the RTP level of voice over IP. Most people deal with SIP and try to make that secure, or they look at maybe SRTP and key exchanges and stuff. But the old stuff which is there, not many people look at it, and then, well, it creates a few problems. Okay, so if you have any equipment to test, like some non-open source RTP proxy that you want to test, just drop me a line. Maybe I should have written my email address somewhere. Just if you want to get in touch with me, you can, just send an email to kpj@googlemail.com. And I will also upload the slides to the Pentagraph system, and then you also include the email address there if you have something that you want to test. And yeah, if you got questions, then thanks.
Hi, I did a presentation about similar topics yesterday, and the situation seems to be worse than I expected.
Well, it's good opportunities.
Pardon?
Good opportunities. It's
yes.
not worse.
I did similar tests a couple of years ago with a closed source back-to-back user agent, and it really fixed the mapping from IP address and port number. You have to be the first one who sent the RTP packet to get the traffic redirected, which is a very short time frame. You have to know when somebody calls, and it's not so easy.
That's sufficient to fix it, I think.
We are currently introducing a new back-to-back user agent. I think I have to do some more testing here.
Yeah, it's pretty easy.
Yes,
send some small UDP packets.
Yeah. But I'm impressed. It's really worse than I thought. Yes.
Okay. Anybody else?
Anybody else?
There's somebody.
Yeah, we have another question.
I'm sorry if I didn't hear, but is your code, your RTP jam and DTMF jam available online anywhere?
No, and it probably won't because it's very messy, but you just have to send those very simple packets every few milliseconds, and that should be doable. And if you're not capable of doing that, you shouldn't be doing it because you can cause quite some audio problems out there.
Any more questions? So I guess let's thank the speaker again and we'll call it a day. So this